Welcome to This Explainer. Look around you right now. The chair you're sitting on, the screen you're looking on, the vehicle you use to get to work. Literally everything we rely on in our modern world is the result of mass production. But, have you ever actually stopped to think about how billions of parts, manufactured in entirely different factories all across the globe, actually manage to fit together? Well, today we are going to uncover the fascinating hidden rules of engineering that make our physical world function. We're talking about tolerances, limits, and fits.
So, this begs a pretty massive question. What makes mass production actually work? It is incredibly easy to just assume that machines cut metal or mold plastic perfectly every single time. But as we're going to see today, perfect parts are actually an engineering impossibility. The real secret to mass production isn't perfection at all. It's a meticulously calculated system of controlled imperfection. Here's our roadmap for this explainer. We'll start with the magic of interchangeability, then look at the reality of variability. After that, we'll dive into tolerances as a buffer zone, how we go about setting the limits, and finally, allowances and fits. Let's jump right into section 1, the magic of interchangeability.
Okay, imagine a standard cylindrical housing, kind of like this one, sitting on an assembly line. Or maybe it's sitting in a mechanic's shop as a replacement part. For mass production and global repair networks to actually function, this housing absolutely must be able to accept its internal components seamlessly. No custom filing, no manual adjustments, none of that. Now, pair that housing with a linkage designed specifically for it. Because of interchangeability, this exact linkage could be manufactured in a completely different country at a completely different time, and yet there is no doubt it will still drop perfectly right into that cylindrical housing. It really is kind of magic. So, to put it formally, interchangeability means parts match any assembly of the same type, no matter where or when they were made. When strict global standards are followed, this whole concept minimizes repair time, allows for super easy replacement of defective devices, and, this is key, drastically reduces the specialized skill required by an assembly line worker or a mechanic. Moving right along to section 2, the reality of variability. We're essentially looking at two very contrasting realities here. In a world of low manufacturing variability, highly consistent processes mean parts fall right within specified limits, and universal interchangeability totally thrives. But if you introduce high variability, suddenly parts just don't fit. The exact moment a part is too large or too small, boom, it loses its interchangeability. It suddenly requires manual modification, like filing or machining on the spot, which introduces a huge risk of failure and completely bottlenecks production. And that brings us to a stark, unavoidable reality on the factory floor. Perfect parts are physically impossible. Let's say a blueprint calls for a 20mm dimension. Well, natural variability in the cutting machines, the daily wear and tear on the tools, and even human operators mean that producing two parts that are perfectly, exactly 20.000 millimeters is literally impossible. The real size is always going to vary. Now, before we solve for this variability, let's get our terms straight. In limit systems, engineers simplify the physical world into holes and shafts, but we are just talking about literal pegs and round holes here. A hole is any internal containing space of a part, the feature receiving another component, and a shaft refers to any external contained feature, the physical material that goes inside that space. All right, section 3, tolerances, the buffer zone. Because reality is imperfect, engineers basically have to hack the system by creating an acceptable buffer zone of error, and we call this tolerance. It's the difference between the maximum and minimum limits of size. So if a part is allowed to be as large as 20.05 millimeters and as small as 19.95 millimeters, the tolerance, that total permitted variation, is exactly 0.10 millimeters. Now you might be wondering, why does this matter so much? Well, it's a massive balancing act. First, it acknowledges variability, admitting that exactly identical parts just don't exist. Second, it ensures functionality by defining a safe zone where the part still works flawlessly. Third, it enables that magic of interchangeability we just talked about. But this final point is absolutely crucial: controlling costs. Why not just try to make everything as perfect as possible? Because tighter tolerances require incredibly expensive, high-precision machinery and way slower production speeds. Wider tolerances are simply much cheaper to produce. An engineer always has to balance safety and function against the real-world realities of a manufacturing budget. Engineers typically map out these tolerances in two different ways.
Bilateral tolerance allows variation in both directions from the basic size, so a little bit larger or a little bit smaller. This is your standard approach for general manufacturing. Unilateral tolerance, on the other hand, allows variation in only one direction, either entirely positive or entirely negative. And this is an absolute must for precision mating parts, where an error in the wrong direction would literally cause two parts to crash right into each other and fail.
Which brings us to Section 4, setting the limits.
So instead of giving a machinist a basic size and asking them to add or subtract the tolerance in their head, engineers often use something called limit dimensioning. This method directly states the maximum and minimum permissible sizes, usually stacked right on top of each other straight on the blueprint.
The benefits of doing it this way on a busy shop floor are huge. It absolutely prevents operators and inspectors from having to do on-the-fly math. In high-volume production, where thousands of parts are churning out every single hour, even a tiny mental math slip-up can lead to an entire batch of wasted parts, which we call scrap. Limit dimensioning is a completely foolproof way to communicate exactly what is acceptable.
When setting these limits, you're often going to see an M inside a circle on a technical drawing. This stands for Maximum Material Condition, or MMC. And it's exactly what it sounds like. It's the point where a feature contains the absolute maximum amount of physical material allowed by its limits. Basically, the part is, quite literally, at its heaviest.
Now, this concept gets really interesting when you compare shafts and holes. For a solid shaft, the maximum material is obviously its upper limit. A bigger shaft simply means more metal. But for an empty hole, the maximum material condition is actually its lower limit. Think about it. A smaller hole means less material was drilled out, leaving more physical material behind on the actual part. Engineers calculate MMC to guarantee that even at their absolute bulkiest, two mating parts will still successfully assemble. And of course, the inverse of this is the least material condition, or LMC, represented by an L inside a circle. This is when the part is at its absolute lightest, the lower limit for a shaft and the upper limit for a hole. Now, why do engineers care about a part being at its lightest? Because they use LMC to ensure a part maintains a safe minimum wall thickness. They have to guarantee that even at its thinnest allowed limit, the part retains enough structural strength so it doesn't just snap under pressure. And finally, Section 5, allowances and fits. We have talked a lot about tolerance today, but we really have to contrast that with allowance. Tolerance is the acceptable error allowed on a single individual part. Allowance, though, is the intentional, designed relationship between two parts at their maximum material condition. It's the minimum hole size minus the maximum shaft size. Essentially, it is the deliberate gap or lack of a gap engineered right into the blueprints from day one. That allowance results in two main types of fits. If the allowance is positive, meaning the hole is intentionally designed to always be larger than the shaft, you get what's called a clearance fit. These parts can slide or rotate freely relative to each other, kind of like a piston moving in a cylinder. But if the allowance is negative, meaning the shaft is intentionally engineered to be larger than the hole, you get an interference fit. These parts will not just slip together. No way. They have to be mechanically forced or pressed together, locking them permanently in place using friction. As we wrap up this explainer, I want to leave you with a thought. Look again at the device you are watching this on. How many invisible tolerances, how many perfectly calculated positive and negative allowances are holding it together at this exact second? Mass production isn't magic, and it certainly isn't perfect. It is the brilliant, hidden mathematics of managing imperfection, ensuring that everything in our engineered world fits exactly as it should.